building on what we talked about in the previous section, we're going to look at the idea of the escape speed from a gravitational object. And the condition for escape is the kinetic plus the potential is equal to 0. The reason this is that we know that the potential energy goes to 0 out at infinity. So if I go ahead and I draw my energy curve, my potential energy, it goes to 0 way out somewhere at infinity. And if we draw in the associated kinetic energy, in order for this object to escape, it has to have a kinetic energy that allows it to essentially reach infinity. And so if k plus u are equal to 0, oops, I didn't mean to cross the line there, this kinetic energy will get closer and closer to 0 as this line comes up. And so essentially once you're infinitely far away, you will come to a stop. But since you never reach that far, it's not really a big factor. So this is just another way of saying that the total energy is equal to 0 in order for the minimum escape condition. Now, the energy bars can really come in handy when solving problems. The energy graphs obviously serve a role, but the energy bars are actually a little bit more useful. So let's say that you have an example of an object on a moon of radius r, and that object gets launched by a spring or something. We don't want it to be a rocket. We just want something that gets launched with some initial kinetic energy. And we want to know what sort of V initial we need to have so that when we're infinitely far away, we have some value V final for our speed. So what we can do is draw our energy bar charts here. We're going to have K initial plus UG initial plus the work is equal to K final plus UG final. So just a couple things to keep in mind. So UG initial, even though this is on the surface of the moon, what really matters is how far that surface is from the center. So we're really starting at, say, some radius here. And so we start off with some negative potential energy. Now, if we choose our system so that there's nothing external to it, there's not going to be any work done. And so that means we can just ignore this term. And we need to figure out what exactly does our K initial need to be if we're going to have some K final. Now the key is it has some final velocity when it's very, very far away. And by very, very far away, we essentially mean that the potential energy final has gone to 0. So in writing down our energy conservation equation, this term and this term are 0. We just have that K initial plus UG initial is equal to K final. We can go ahead and we can solve for this unknown velocity here. So this section really introduces this idea of escape velocity. And one other thing to pay attention to is the definition of bound and unbound states. And although this section doesn't talk about it, we should introduce the idea of a trapped state. So if really for the bound state, we have that E is less than 0, the total energy is less than 0. This is the bound. For the unbound state, we have that E greater than or equal to 0. And then the trapped case is a special situation where the energy is greater than 0, but the potential prevents something from leaving. And this you can see if you go back to the previous section. If you go to page 255, figure 6.41, there's a potential energy curve that looks something like this. And if you have a total energy, a different color, if your total energy is right here, then you've got some forbidden regions. So right here, here, and here is where the potential and total energy are 0. The kinetic energy would be negative in this region and in this region here. So if you had a particle that started out in this region with an R equal to, say, one of these values in here, that particle would essentially be trapped in here, even though it satisfies the condition for being unbound. So this would be an example of a trapped state, simply meaning that even though the total energy may be greater than 0, the potential prevents it from escaping from some region, or if the particle started out here, had a radius out here, it would be prevented from entering that region.